Okay, this is going to be fluid mechanics exam 1 review. So our first exam is on chapter 1 and chapter 2, which means we're going to be covering the topics of fluid properties, sliding plates, the appendix problems, fluid height from pressure, not even from pressure I think, from just shear, strain, and stress. Here we're going to have height from pressure, pressure in a system at a point, force in a chamber, fluids acting on an object. This is the big part of chapter 2, fluid statics. Buoyancy, fluid in motion, height with centrifugal force, and lastly we're going to go over some definitions. So I want to just like hit on one of each, except for sig-fig conversions. That's like not really something we should go over, but I want to go over things that we might not have gone over. All the underlined ones are from my videos, so yeah, let's see. So yeah, these are the equations we'll use, by the way. Pause and make good note of these. Okay. Chapter 1 problems. Looks like we can start with, let me see. I want to see what does 1/8 look like. 1/8, 1/9. I know the one I want to do. 1/12. Might be not even 1/16. I can just find it. That one's 36. I guess we're gonna. 536. I don't see it on my thing. I think I might have accidentally. Chapter 1. Oh shoot, I'm on the on chapter 2 problems. I was about to say. I couldn't find the one I was looking for. 8, 9, okay. Number 12. This is going to be chapter 1, problem number 12. And we're given swimming pool like this. You know, this dimension, this is 9 meter by 4 meter. At depth equals 3.03 meter. And that's at t equals 5. And we're asked to find depth at t equals 35 c. Okay. Now pretty much the the only things we need to know here is that it's going to be the same mass because it's the same fluid. Not that it's both made of water. I mean, it's literally the same exact fluid. We're not adding or removing any water. So whatever the mass is originally, it's what the mass is going to be at the end. And the next thing we need to know is that m equals density times volume. Now, what's going to change here? The mass is going to stay the same. I believe that the density will change and this will change. How would the mass stay the same? Because the volume here is going to be length times width times height, or in this case depth, but I'm going to call it height because this is basically just a big rectangle. So that's how this is going to work. This is going to be the thing that changed. This is set and this is set. The depth is the variable here. So let's first find m at 5C. The density of water at 5 degrees C, if I remember correctly, I could just look at my worked example here. I think that's just going to be the 1,000, the straight 1,000 kilogram. No, not quite actually. In the appendix of the book, though, which I should actually just be looking at, it is the 1,000. Kilogram per meter cubed times our volume, which is 9 times 4 times 3.03. Okay. And this is going to be 1,000 times 9 times 4 times 3.03. 10, 90, 80. Okay. That's in the kilogram. And now the m at 35C is going to equal, well, at 35 degrees, this is going to be 994 kg m cubed times 9 times 4 times h. Now remember that this mass is the same as this mass. So what we can say is that 10, 90, 80 is equal to this. So what we could first do is divide this by 994. So we're getting 109.7 is equal to 9 times 4 times h. 9 times 4 is equal to 36. So now we're going to divide this by 36. We're getting 3.048 equals h. This is meters. And that is the solution to number 12. Okay, nice. That's one smiley face down. And one more problem covered. Now the sliding plate problems. These can get a bit tricky. I don't want to necessarily do a new one for each of these because I picked the examples for a reason. Some of the problems that were given out in this chapter were just a bit much. I think they will not be seen on a test. They're good to know and understand and do for homework, but like they're too involved. So now we've got our choice 30, 31, and 32. Okay, so yeah, for this one, I mean, this is probably a good one. 32, 31 is probably a good one. Let's see. German. I mean, 32 and 30, they're both actually not bad. Probably pretty involved, as I said before, but let's try. I mean, 32 seems like the better one because it's determine the minimum shear stress in the fluid. That's probably the better one, but gosh dang, I think that's the one. I don't know. I think it's the one we do. Okay. So given this little U looking thing, I believe is what that is. No, they used, oh, they're so stupid. They're so stupid. Why would they do that? So I've got a problem with this. They've got a squiggly U and they used U for a variable. Use anything else for a variable. Why would you do two things that look so similar? The normal U is 12y to the fourth, 1 over 4, the quarterth, and mu is 0.5 e negative 3 Newton second meters squared. And this is what the diagram looks like. Just like this, and you know this is 24 millimeters a second. So we know our velocity, and we are told this is at a depth of 16 millimeters. Okay. So what's the equation we use here? From this equation sheet, we know that this tau equals mu du dy. So I think we can plug this straight in for du, but we might actually, or sorry, for dy. That's the velocity on the plate, force on the plate. It looks like we don't know that. Minimum shear stress. Now that's the big part of this, is we need to know how to get, what is the meaning of minimum shear stress here? Oh yes, this is going to be what our y is right here. Okay. Oh yeah, so you do have to do du over dy. So this is like an integration problem. So we have our 12y to the 1/4. We're going to move this in front, so it's 1/4 times 12y, and then we're going to subtract 1 from here. So this is going to be 3y to the, what's 1/4 subtract 1? I think it's going to be like negative 3/4. And now we plug in our y here into this. It's going to be 3 16e to the negative third to the negative 3/4. And this is what our du over dy is going to equal. We know what our mu is equal to. So now tau is equal to 0.5 e to the negative third times this. All right. So let's plug it all in then, and hopefully we should get the right answer. Not quite, not quite. Jeez. You break this up in 100 different ways, you get 100 different answers. Is it gonna be the whole thing? Maybe 3 times 16 e to the negative third to the negative 3/4. Nope. I knew this one was. It's a good one. I don't get where I'm messing up here. So we did du. This should give us tau. Straight up. I'm pretty far off though. Should y equal 16? Is it really that simple? Nope. Okay. Okay. So yeah, I wasn't joshing with myself. This is correct, but you have to format it so specifically. So what you have to do here is it is 0.5 e to the negative third. That's correct, okay? That's all good. But this right here, this is where everything gets messed up. It's actually 3 times 16 negative 3 quarter e to the positive third. I tried it about 100 different ways. This is how you have to do it. So I'm gonna have to remember that. That's But if we just convert everything to meters right off the bat, it's probably much easier. So let me try to do that. So 16 in millimeters equal to like 0 point, it's just 0.16. Okay, it's 0.16 maybe? Let's see. If we go to apps, 0, SI tools, unit converters, SI prefixes, 16 milli becomes, yeah, e to the negative 2. So I think that's this, and then is there any units? I should have wrote those. This is like millimeters per second. So this is, again, 1 millimeter becomes 1 milli e to the negative third base. Either way, the tricky part of this problem is the formatting. This is a bit of a tricky thing. I think I'm just going to try to rote memorize this because the formula is fine. And if you're given u, you can make it du dy in terms of y, and then plug y in, which means we could also do 31. Hopefully now that should be much easier. So problem 31 is same thing. We've got this situation going on with the 24 millimeters a second, with the 16. We also have this, which is height y. We're given that u is equal to, that's why they used u, by the way, because that's in the formula. And then they say take y to equal 8 millimeter and mu to equal 0.5 e to the negative third Newton second per meter squared. And I didn't write this down, this is millimeters per second. So we could immediately try to get this in meters per second. I think we could try that. This is going to be 0.008. And this is going to be 0.012. Or, like I said, I could just do the rote memorization thing. So we know that tau is equal to mu du dy. We can just derive this, which we already did. That's fourth. That's our 12th. Y. This is going to be 3y. Negative 3 over 4. We know y is equal to 8, so this is going to be 3 times 8. Negative 3 over 4. Tau equals this. Now this is going to have to be multiplied by mu, so tau equals 0.5 e to the negative third times 3 times 8 to the negative 3 fourths, all that e to the third. Okay, and for this one, which is problem 31, I'm getting the correct answer. Nice. That tau is equal to 0.315 or 0.3 MPa. I should make careful note of that. In my one right here. Okay. So now we've done these two. And how is number 30 done, by the way? Let me take one more look at that. So that's the tau equals F over A. I remember that. That one was a lot easier, I thought. Because you're pretty much given everything. You just got to plug and chug. But he also said that we won't be using calculus on this exam, that you won't be using anything crazy. So I'm assuming we're probably in the good right there. And appendix problems. Let's do number 54. All right. I doubt we'll be getting an appendix problem, so number 54. water flows through pipe, kind of comes down a little bit like that. We're given that temperature equals 20°C. Determine the lowest absolute pressure it can have without causing cavation. So we go to the appendix, and at 20 degrees C, vapor pressure is 2.34 kPa. I'm assuming that's the answer. You just find the vapor pressure. So this is lowest P before cavation. That's all. They're so stupid. I mean, hopefully we get something that's stupid, but cross that one off. Now we have fluid height problems. Let's do. We did 60. 61 is plotting. 62 is plotting. So that's six. That's down. We only have 59 left. It's plotting, so I won't do any of those. I could go through 60 again. The only one that you don't plot a graph. D equals 0.12 inch. Temperature equals 68F. We're asking find H. And we know from our formula sheet that H is equal to 2 stress cosine theta over rho GR. So H is going to be equal to 2 times, well, what's the stress of mercury at this nonsense? That's in newtons. We want it here, so this is going to be 2 times 33.3 e to the negative third cosine of, I think this is going to be 180 minus 50. It would be 90 minus 50 though. Let me check later. I think it's 180 minus 50. What would that even do? Taking it from here. Yeah, I get it. It's from the vertical. Times rho GR. We know the density of mercury is going to be 26.3. Gravity is 32.2. R is going to be 0.12 inch divided by 2 divided by 12 to get it into feet. I think we should do it in foot because everything else is in foot. Alright, now we plug it in, and this is another thing where hopefully I can just get it in the calculator correctly. Whoops. Why? I want to make another one. There we are. 0.12 over 2 over 12 equals negative 0.0101 foot. Now, is that problem is this? 60? That's 61. And then times 12 to get it into inch. Negative 0.1 inch. That's the problem. If they want it in inches, which they probably do, but amazing. That is all of chapter 1. That is literally already did the problem. So chapter 1, 2 thumbs up. We actually didn't do the problem with that. That would be back in fluid properties, but you know what? You know what? That's alright. For now. Alright, chapter 2. I've covered like everything so far. There's not much left. Not much left. I want to do one of these. I want to look at one of these. I can't solve these. These are crazy. These are way too crazy. These are too crazy. One of these is too crazy. So pretty much I've already done all I could with this. So let's just try to get through this really quick. And yeah, I'm going to definitely just be redoing stuff because I did so much of this chapter. Problems 1 through 45. Let's find the one pressure one that I was looking for earlier. $36. Only one I didn't do. This one's a bit of a bear. You can do this one. I think you've got the whole thing. Point B. This is 3.5 meters. This is all water. All of this that I'm marking, that's all oil. Oil suspended through 2 things of water, and we've got this, they call it H. We're given, this is 0.5. This is 0.75. And this is 2 meters. And like, there's a spigot. And we're told that H is equal to 2.25 meters. PB is equal to 600 kPa. And we're told that rho oil is 900 kilogram per meter cubed. Okay. Let's list off all of our points. Point A at the bottom. I think that's point C right there. Point D right there. A, B, C, D. Why'd they do it like that? Why can't they just follow one way or the other? Who knows? They hate us is why. Okay. So we can start anywhere. We can start, they want to know the pressure at A, so we can start at B. Alright, and then pressure at C is going to equal, remember, P equals rho G H. And we're going to have to determine positive, negative system. So pressure at B is this. Going up, I was going to say is negative, so negative. This is all water from B to D. This is going to be 1,000 times 9.81 times 3.5. 34,335. That's a negative. Let's add this to our 600. I'm hoping this is the correct way of doing this. Remember, this is also plus EB. Okay. Pressure at C is going to be equal to, from here to here, we know is distance h. This is going to be negative because we're going up. 900 times 9.81 times 2.25 minus P plus B at D. 19,865 plus negative 33735 13,869.5. Now we get P at A. It's going to be water again, 1,000 times 9.81 times 0.75 plus 2, so 2.75 plus PC. 1,000 times 9.81 times 2.75. 26977.5 plus whatever our other thing was. 13107.75. Really hoping that's right. It's not right. Okay, well, we'll try it again from the other side. I don't know. I don't think we should try it from the other side. I like that. What happened wrong? That's a good question. What happened wrong? This one's the hardest one of them all. Oh, okay. I see where there's one mistake. That doesn't throw anything off too far. Oh, oh shoot! Is it really that simple? This is gonna be all in PA. That's in KPA. Well, let's see. I think it might just be that simple. Let's just divide each of these by 1,000. 'Okay. So now, taking it from here, it's going to be 600 minus 34 minus 19 plus 26. 572.7. Hot dog, the correct answer is 573. All right, so then what was the mistake that we made? All of these answers were in PA. This one right here was in KPA. That's the only mistake we made. Plus, I actually kind of like doing it this way and then figuring it out later instead of trying to think of positive and negative. You can just get the answers now and then trace it later. So actually, that's a smiley face. The mistake wasn't in concept, it was in execution, which is a much better mistake to have. Okay, nice. Nice, I feel good. Yeah, I'm just gonna do one of these. So, 47. Foot, 6 foot, 60 psi in the system. We're asked to find the force on the bolts. Pressure equals force over area. 60 psi equals F over pi. I don't know, 6 times 12 by r squared. I think that's actually it. 60 times pi 6. Now is it times 12? It's going to be times 12. $977. What would the answer there be? PSI? No. Kip. It was over 2. That's why I did that. Okay. $60, because that's diameter, not radius. 60 times pi 6 times 12 over 2 squared. Oh, sorry. It's 5 foot. I was about to say, this answer is like, it's off, but I know I'm right. Here we go. 5 foot. This means that F is equal to 1696.46. Divide this by 144. And, or sorry, 1000. We're getting 170 kilopound, because this force is in pounds. Duh. And then let's do it for the other one. 60 psi times pi over 3 times 12 over 2 squared. $61 kip. It's 47 done. Let's do. I think 109 sucked. I don't know if I want to do that. $58 was. I can't believe I solved. I solved 58. That one was terrible. I hope we don't get a gate problem. Yeah. Was 109 the wall? No. That one also sucked. We're never getting stuff like that. Those are terrible. Buoyancy. I do one. 121's impossible. Number 54? Maybe? No, I don't want to do it. I don't want to do it. I did 48. Yeah. I mean, those ones are too time consuming. I'll take a look at them, but I'm not going to do them. I mean, I might do 48. Screw it. So we need to know the FH and FY equations, which I don't have written down. So I guess I won't do this. Mental note, freaking write down FH and FY equations for this specific problem. This one was really quick to do, so I'm assuming this one probably will be on the exam. And yeah, fluid in motion. I don't really need to do the one with the truck. I already did that before. And the other one with the glass, where it's here and it does this. I think I'm kind of just done. I'm calling it. I don't want to overstudy or overwork this. I'm feeling good. I want to eat some lunch instead. And we have a nice and well fed for the exam. All right. Peace.